Let's resume the discussion about the integrability of random variables, starting from the lemma that we saw last time. So a random variable x is integrable if and only if the limit as b goes to infinity of the expectation of the absolute value of x restricted on the values in which the absolute value of x is it should be more properly said restricted on the set in which the domain of the absolute value of x is larger than b, I think. Well, this thing goes to 0. And we saw the graphical example and the proof of this proof. Let zb be the absolute value, this truncated random variable, even if I didn't understand very well why we call zb if we then keep using the entire random variable. Well, we call it for the final part probably. Okay. And notice that this thing is bounded by the absolute value of x. And it goes to 0 as b goes to infinity. Now, since x is integrable, we can use dct to say that the limit as b goes to infinity of the expectation of the absolute value of x when it is larger than b. Well, how can I actually say this? The absolute value of x restricted on the domain in which restricted on the set in which the domain of the absolute value of x is larger than the threshold b. Well, we can say this is equal to the expectation of the limit and this thing goes to 0 because x is integrable. So this should be like a consequence of the integrability of x. Now, for the other way around, suppose that this thing holds, so that the limit as b goes to infinity of the expectation of the absolute value of x restricted for values larger than b is 0. Then we can choose b large enough or small enough, actually small enough well, it depends on how you see it. We can choose b, here it says large enough, but actually we make it smaller, I think, because if this area is 0, we want this area to be 1, so we choose a smaller b, such that the expectation of zb is bounded by 1. And we know that the absolute value of x is bounded by b plus kb, right? No. B plus zb. Why? I don't know. So the expectation of the absolute value of x is bounded above by this thing, which is bounded by 1 plus b, because this is bounded by 1. Yeah, here we can see it as the expectation of zb. Okay, we can choose b right now. We know this thing, so this is bounded by 1 plus b, which is finite. And this concludes the proof. Okay, I think we did a bit better than last time, even if there are still some details that are not completely clear, but let's move on now. And we saw we saw the definition of uniformly integrable collection of random variables. So we say that a collection K of random variables is uniformly integrable if and only if K of B, which is the limit as b goes to infinity of the supremum over all the random variables in the collection, such that the expectation of the right tail of these variables goes to 0. Well, this is the definition basically. And we also saw some remarks. So K finite, each x integrable implies that K is uniformly integrable. Second, if K is dominated by a random variable z which is integrable, then K is uniformly integrable. And then we saw this, that uniform integrability, UI, implies L1 boundedness. How is this possible? Well, by this we mean that the collection K is in L1, is L1 bounded. Now, my question is, what is the difference between being in L1 and being L1 bounded? Because by L1 we know L1 is the set of functions whose absolute value is integrable. And by L1 bounded, what do we mean? In any case, let's continue. So let's try to take a look at the proof of this. I don't remember anything, so let's just rewrite it. The expectation of an absolute value of x can be bounded by b plus k of b. where k of b is basically what we called the expectation of zb in some way. K of b is this thing here. And again, why is it a function of b? I mean, we let the parameter change, but this is true for any x in the collection. Now, since each random variable is in k and k is ui, since any x is in k uniformly integrable, we can use the uniform integrability of k to choose a value for b. We can choose b such that k of b is bounded by 1. It is quite a similar reasoning from the previous proof, I think. I mean, we are doing basically the same. But in this way we can... we should exploit uniform integrability in some way. So you can construct a further bound for that b and prove that the expectation of the absolute value of x is bounded by 1. For all of them. And then if we take the larger b, we have proven L1 boundedness. I mean, this looks basically the same proof as above with some different things. So we have proven what did we prove? We proved that the expectation of x is less than b plus k of b, which is less than b plus 1. No, it's simply less than this. And this means that we give a uniform bound for all the random variables in the collection, and then by uniform integrability we give a uniform number, so we have bounded to blah blah blah. So this gives, okay, so this is basically the proof. Okay, and well, basically we left here. Now we can see that the converse is not true. That is, that L1 does not imply uniform integrability. And we will use a counterexample. So consider as a space probability space, the interval 0, 1, the Borel sigma algebra on the interval 0, 1. Well, here it is written like this. And the Lebesgue measure. And the collection K of random variables such that xn is n when omega is less than 1 over n and 0 otherwise. Let's write else. So this is the crucial thing we have to remember for this example, for this proof. And this was actually an exam question. So, for any n, the expectation of xn is 1. Why? Because it's a Bernoulli random variable, and the expectation of a Bernoulli random variable, I never remember, should be expectation here of xn n times, well, this n times 1 over n plus 0 times 1 minus 1 over n, and this simplifies and gives 1. So we can say K is L1 bounded because the integral of each random variable is bounded. I still don't understand the difference between simply L1 and L1 bounded. But what happens here is that K of B is 1 for any B because the expectation of xn restricted on values larger than B. But here the absolute value is not really necessary since it's a positive random variable, is the same thing as the expectation of xn. Why? So we found a sequence whose expectation is finite, but whose expectation does not go to 0. So the collection is not uniformly integrable. What is x1? X1 is 1, 0. When omega is less than 1. Okay. Well, let's continue. One other important thing is that LP implies UI. And to prove this, we use the following proposition with f of x equal to x to the power p. Proposition. Suppose there exists a positive Borel function f on R plus such that the limit as x goes to infinity of f of x over x explodes. Right? See, yeah. And write C as the supremum over k of this thing here. The expectation of f applied to the absolute value of x, which is finite. Actually, let's put it like this: if c with blah 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 is finite, then k is uniformly integrable. Let me correct it here. So we have a positive Borel function with this form here, and we notice that the supremum of the collection of the expectation of the function applied to the absolute value of each variable is finite, then k is uniformly integrable. Proof. Here it says without loss of generality, assume x is a positive random variable and replace f with with let's put it like this. The maximum between f and 1, where f is greater than 1 or equal. Call g this function here no, this thing here. And note that x truncated for values larger than b can be written this way, which is quite strange. If applied to x, g applied to x again, because if applied to x is f of x times x over f of x, which is x. What is the meaning of this? And now we bound this quantity, I think this one, by f of x, the supremum x larger than b of g of x. And if x is a real value random variable, most surely we can rewrite the bound as so with the absolute value. Here we didn't have it. Now take the expectation and we should have this. And for b going to infinity, and so x going to infinity, the term supremum should be good. This thing should be going to 0. because g of x is x over f of x or in other terms 1 over f of x over x. And here it concludes saying that k is therefore uniformly integrable. So what are we doing in this proof? In this proof, how are we using this result? We use this function, we check that the supremum is bounded, and we conclude that it is uniformly integrable. Oh well, but this is the proof for this proposition, not for that thing there. I think. Oh no, yeah. This is the proof of this. But we didn't take f to the x to the power p as a function. But x to the power p satisfies this thing. So we have a positive Borel function and this, like for example, the limit is x goes to infinity of x to the p over x goes to infinity because of the power. And so here we assume that x is positive. We take this function here, y. We call g in this way, y. We rewrite x in terms of f and g. And then we apply the theorem, the proposition. Now I don't know why we have this c here. We consider this just as a constant, maybe. But why? Because we take the expectation and this is some value. And with this, we conclude the proof. E poncio. And let's start talking about sigma algebras generated by a random variable. So consider x taking values in the space E. We call sigma x the set the set of all preimages of all preimages through x of A for all the events or sets A in the sigma algebra E. Correct. And this is written also in this way. an important remark of this is that if we call G the sigma algebra generated by X, this is the smallest sigma algebra for which X is measurable. Relative to X and G, relative to G and E. And now we can call the sigma algebra generated by a collection of random variables. So if we have xt, taking values in et script et, then the sigma algebra generated by the collection is the following one. It's sigma of xt with t in the index. Oh. Che brutto. This thing is the sigma algebra generated by the union. But this is denoted also in this way. And this is the sigma algebra generated by the union of the xt. The sigma algebra generated by the union of the sigma algebras. And the notation that is commonly used is this one. And the idea is the following: since unions of sigma algebras are not necessarily sigma algebras, we first consider the sigma algebra generated by each one, we take the union, and then we generate the sigma algebra on that union. And here we have a first proposition, or property if you want, which is simply an observation. If X is a collection of random variables, then the sigma algebra generated by this random variable is the same as the sigma algebra generated by the collection. And well, here usually the notes write for T in capital T, but I just leave it. It's more comfortable in this way. And with this said, we should now start talking about monotone classes of functions which allow to check measurability for a family of random variables, a family of functions in general, as far as I know. Monotone class of functions. So a collection of functions M is called a monotone class if it contains all the indicators and by this I don't really know what we mean, then given F and G yeah, there is a typo here in my notes. Given F and G, which are measurable and bounded with respect to M, and A and B real numbers, we should have that AF plus BG is still in the collection. And thirdly, given a sequence of functions in the collection, which is increasing to a limit f, this should still be in M. Well, the limit is in in M. Okay. And I think we can take a break now and continue next time. We actually finished the first page of the notes, the first 2 pages actually, and next time we will continue with Morton class theorem for functions, which is quite long. And let me see. Yeah, from here things will start to get even more complicated. So let's try to collect some more energies for the next session.